right, so let's do this. So let's start with quadratic equations, and we're gonna solve them. So we're gonna be solving quadratic equations by, so either we're gonna be factoring them, and we've done this already, so this is not nothing new with the factoring, or we're gonna do by taking square roots. So that's why the topic for radical equations comes before this, because we're dealing with square roots a lot when we talk about, we may deal with a lot of square roots when we solve quadratic equations. Okay, so again, some of this is the review from the previous units, right? So if we want to solve, for example, 3x squared equals 2 minus 5x, right? This is a quadratic. This is a quadratic equation. And what's the first thing we do for quadratic equations? What must we do to set it up for us so that we can solve? Anybody out there? That's right, David. We make it equal to 0. That's right. So we subtract 2. Subtract 2. We add 5x. We add 5x. So then what happens when we do that on the right side? Cancel, cancel, right? And we get 3x squared plus 5x minus 2. We have that on the left side of the equation, and we have 0 on the right. So this is what we have. That's what we normally do, right? We set equation equal to 0. And whatever that entails for us to do, we do. Okay, now once we have that, this becomes what? A quadratic, a trinomial, right? So what can I do? I can think, hey, can I possibly factor this? So if possible, factor. And we can. 3 times negative 2, we've done this a lot, right? Is what? Negative 6. What multiplies to negative 6 adds to positive 5. What are two numbers? 6 and negative 1. That's right. So positive 6x. Let me write this in different color. Positive 6x minus x. Minus positive 6 times negative 1, negative 6. Positive 6 plus negative 1, positive 5. And then we go on our merry way, right? We factor by grouping, and we get 3x. We get 3x, x plus 2. Factor out the negative 1. We get x plus 2 equals 0. Then we get what? X plus 2, 3x minus 1 gives me 0. Solve for each. Solve for each. So I get x equals negative 2 and x equals 1/3. And we did it. So then what are the roots? What are the zeros? The solutions. What is it? Well, it's x equals curly brace negative 2 comma 1/3 close curly brace. So that is something we've done before, nothing new. We've done this before, right? We've done this. So these kinds of quadratic equations we've done. Factoring them, we've done. Okay, so we've done those, but we haven't necessarily had too much experience yet with using what's called square roots to solve. And we use square roots when we have a particular expression. So here we have a quadratic, right? And when we set it equal to 0, it forms into a trinomial, which may or may not be able to be factored. In these cases, they are factorable. But we sometimes have quadratic equations that don't look like trinomials. For example, let's look at this. 3x squared equals 54. This is also a quadratic equation. Why is it quadratic? The moment you have an x squared in it, and that's the highest term, it's a quadratic. But what you notice is you can't create a trinomial. So you can't create a trinomial with this. So whenever you don't have a trinomial, you can think of another way of maybe attempting to solve this quadratic. So for example, I want to know what x is regardless, right? I want to know what x is. So what do? I divide first by 3. So I divide both by 3 first. And when I do that, I get x squared on the left side. And 54 divided by 3 is, I believe it's 18. And now, look what we have here. We have to what? Take square roots. Square roots on both sides of equation. You see here we're not going to factor. We're going to take the square roots. What we have to do, though, is be extremely mindful of the fact. So note, the square root of x squared is absolute value of x. Important note. Important note. When you take the square root of x squared, there's this absolute value. So in reality, you're saying this when you do that. Absolute value of x equals the square root of 18. What does this mean? This means that x could either be rad 18 or x could be negative rad 18. That is why when you take the square root of an x squared, sometimes people write it this way. X is equal to plus or minus square root of 18. That's where the plus or minus comes into play. Plus or minus. So x equals, because anything inside here could be positive or negative. When you take the absolute value of a positive or negative, you'll always get positive. That's the idea. So x is positive or negative rad 18. And rad 18, can't we simplify this? How do we simplify rad 18? What two numbers multiply to rad 18 where one of them is a perfect square? 9 and 2, very good, Jalen. So we got 9, we got 2, and then square root of 9 is 3. So x is equal to 3 rad 2. Okay. So now we're learning an additional way to solve certain quadratic equations. And these are the quadratic equations that are not in a trinomial form. So when you don't have it in a trinomial form, think about using square roots. I'll give you another example. How about if I have x plus 2 squared minus 24 equals 0. You see, something like this, quadratic. It's a quadratic equation because of the square term. But it's not written in a trinomial x squared plus x plus constant. It's not written in ax squared plus bx plus c form. So when we have in this scenario, we're actually gonna try our best to get rid of that square term. So when we only have a square term, we apply square roots. So now when we add the 24 on both sides, look what we get. We get x plus 2 squared equals positive 24. Now look what we have when we only have a square term. So then let's make a note of that. So on another note, hold on, it's a little too thin. We apply the square root procedure for solving quadratic equations when there is only a square term and a constant in the equation. So that's when we use it. We use the square root idea when you have one squared term and a constant in the equation, and therefore that's when it's appropriate. Notice in the one that we did by factoring, we have a squared term, we have a constant, but then we have this linear term or this term with an x in it. So we have 3 terms. So that's when we can't use square roots. It doesn't make sense to make square roots. But in this case, what do we have? One square term, one constant. And now this new case, we have one squared term and a constant. So applying square roots is more applicable. Makes more sense to use because I want to get rid of that squared term. So I must take the square root on both sides. When I do that, x plus 2 is what happens, is what remains on the left. But remember, the square root of something squared is the absolute value. And so that's where we have to pop out these plus or minus symbols on the right side. So it's plus or minus rad 24. But ultimately, what am I trying to solve for? I'm trying to solve for x, right? I'm trying to solve for x. So I got to get x by itself. So subtract 2 on both sides. So I get x is equal to negative 2 plus or minus the square root 24. But 24 can be broken down, can it? How can 24 be broken down? What two numbers multiply to 24? Or one is a perfect square? What are the only two numbers where one of them is a perfect square that multiplies to 24? Two numbers, guys. One of them perfect square. Multiply to 24. So 1 and 24, that doesn't work. 2 and 12, those aren't perfect squares. What's the next one? That's right, 4 and 6. Square root of 4, square root of 6. Square root of 4 is 2. Square root of 6 is square root of 6. So we get that x is equal to negative 2 plus or minus 2 square root of 6. And this is my solution. These are my zeros. So these are my zeros slash roots slash solution. And that's really the extent of it. Let's see. Yeah, let's do one more of these. So we got 3x minus 3 squared minus 12 equals 0. Do you see this? again, I have a quadratic equation. One term is squared. The other term is a constant. I'm going to use square roots for this. So for this, I need to get the square term on itself, by itself. So I must first add by 12. Add by 12. 12's cancel on the left side. I'm left with 3 parentheses x minus 3 squared equals 12. I must get rid of the 3. Must get rid of the 3. Cancel out the 3's. I'm left with x minus 3 squared equals positive 4. I must get rid of that square term. So I must square root both sides. When I square root both sides of something squared, I must be mindful that there's a plus or minus term on the right. Square root of 4, though, perfect square, becomes plus or minus 2. So x minus 3 is either plus 2 or minus 2. What am I looking for? I'm looking for x. So I must add by 3 on both sides. So x is equal to 3 plus or minus 2, which means I can either have the plus version or the minus version. I can have x equals 3 plus 2, which equals 5, or I can have 3 minus 2, which equals 1. So all in all, the roots, the solution, or the zeros of my equation is x equals, curly braces, either it equals 1 or it may equal 5. And I solved my quadratic equation using roots, using square roots. So if it's possible, factor. If you can't factor, consider maybe using square roots. And that's not always possible. So there's more than one way, there's more than one technique to solving quadratic equations. So these are 2 ways so far. Let me do one more of these. This time I'm going to use fractions because you can also have fractions involved. Let's do something like this. So what if I have x plus 1/3 squared minus a ninth equals 0? So you can have square roots. I mean, you can have radical fractions. What do you do here? I have a square term and I have a constant. I should move the constant on the other side first. The 1/9 on the left side go away. I'm left with x plus 1/3 squared equals positive 1/9. I must take the square root on both sides to get rid of that square term because I want to get x by itself. So then I get x plus 1/3 equals plus or minus the square root of 1/9. What's the square root of 1/9? Isn't the square root of 1 over the square root of 9? Isn't that 1/3? So this equals 1/3. So x plus 1/3 equals plus or minus 1/3. I want to get x on its own, so subtract by 1/3. So then what do I get? Wait, did I? Oh, my apologies. This should be a 2, not a 1. So this is a 2. So I'm not subtracting by 1/3, I'm subtracting by 2/3. And so when I do that, the 2/3 cancel. I'm left with x equals negative 2/3 plus or minus 1/3. So either I have positive or a negative. Either I say x is equal to negative 2/3 plus 1/3, or I say that x is equal to negative 2/3 minus 1/3, right? And when I add it, what do I get? I get x equals negative 1/3. And when I subtract it, what do I get? I get negative 3/3, which equals negative 1. So either my solutions, my roots, solutions, or the zeros, right, is equal to negative 1 or negative 1/3. Okay. Any questions about the square roots procedure step for solving quadratic? No? Alrighty. So next, let's see. So I'll do one more of these, one more, and then we can move on. So what if I have x minus 1/2 squared plus 20, sorry, minus 20 equals 0? I want to solve for x. So add by 20 because I have one squared term, one positive term, so I can use the square roots idea, step, procedure. So this becomes x minus 1/2 parentheses squared equals positive 20. I take the square root on both sides. I get x minus 1/2 equals plus or minus square root of 20. But can I break down 20? What two numbers can break down 20? One of them has to be a perfect square. 4 and 5, that's right, Jeremiah, 4 and 5. So we got rad 4, rad 5. This becomes 2 rad 5. So x minus 1/2 equals plus or minus 2 rad 5. I got to get x by itself, so I got to get that 1/2 on the other side. And what do I have on the left side? X equals, by itself, 1/2 plus or minus 2 rad 5. So I'm done. I figured it out. I figured out what x is. But normally, we can also rewrite our expression as a single fraction. So I can actually rewrite this as 1/2 plus or minus 2 rad 5. Make that over 1. If I add or subtract fractions, remember, when we add or subtract fractions, the denominator should be the same. And in this case, I want to make it into the LCD, which between 2 and 1, the LCD is, or the least common denominator, is 2. So multiply the fraction with the 1 in the denominator by 2 over 2. And I get this equals 1 over 2 plus or minus 4 rad 5 over 2. Now I have two denominators that are the same, which means I can combine the numerator. So this is 1 plus or minus 4 rad 5. And all of this is divided by 2. And there we have it. X equals 1 plus or minus 4 rad 5 over 2. So again, I was done with solving the equation here. Right here, I was done. So you can also write this as my solution, but it's much more conventional to write it. When we have something like this, we would always want to try to write it as a single fraction. So that's where we had to do these additional intermediary algebraic steps. Okay? So that's how you solve quadratic equations using square roots. We've done factoring a lot already. Now we're doing square roots. So if you have those two procedures for solving quadratic equations down pat, the problem is we don't always have this nice of a quadratic equation. I'll give you an example. X squared minus 6x minus 15. Let's look at this. It's a trinomial. It's a trinomial, so square root, this whole square root thing, procedure that we just discussed is not applicable here because we can't take square roots. The problem is we have this x term here, so that's not going to work. Can we factor? So we think about, hey, what two numbers multiply to negative 15 but add to 6? If you go through the factors of 15, 1 and 15, 3 and 5, there's no way to get 6 between those factors. So this is not factorable. So we observe that cannot use square roots, and we cannot factor. We cannot factor the trinomial. So in this situation, what do? Does anybody have a clue of what we do when we have such a scenario? We can still solve it, but we have to use something else. So eventually, guys, I'm pretty sure you guys have heard of it, but when we have a quadratic equation, the way to solve any quadratic equation, I don't care what quadratic equation you speak of, is a quadratic formula. The quadratic formula is bulletproof. You can solve any quadratic equation using the quadratic formula. It's applicable. But before we talk about the quadratic formula, there's a very specific algebraic technique that we must discuss first, and it's called completing the square. So we will solve this quadratic equation using the completing the square method. Has anybody heard completing the square before? Is this a new term? Or have people heard completing the square before? No? Haven't heard of it before? Oh, it's not new. Okay, good. I'm glad. So it should be not too bad, right? So how do we complete the square then? What does it mean to complete the square? What are we completing? Why is it completing the square? What square are we don't have a square. We don't have any shapes here, right? So why do you think it's called square? Is it a square? Anybody? Okay, well, why is it called completing a square? Well, it's not. We can actually can visualize this um, as a geometric representation, and it's kind of cool to see how you really are completing an actual square when you look at it from a visual perspective. But aside from that geometric connection, completing the square, what we're doing is we're trying to complete the perfect square trinomial. So that's what we're doing. When we say completing a square, we're trying to make a trinomial a perfect square one. Um, so the first thing is we want to move the constant to other side of equation. So that means this will be what? X squared minus 6x equals 15, right? We move the negative 15 on the other side. So that's step one. Step two is where we're going to do the completing the square method. This is the completing the square step. So we're going to add both sides of the equation by half by squaring half of the coefficient in front of the x term. So what we do is we notice the number in front of the x term is a negative 6. We're going to take half of that. So negative 6, right? We're going to take half of that, and then we're going to square it. What is negative 6 squared? Isn't it negative 3 squared? What's negative 3 squared? Isn't that 9? So we're taking half of the middle number of the number in front of x, which is 6, half of that and square it. When we do that, we get a number 9, and we're going to add that on both sides. We're going to add that on x squared minus 6x. We're going to add that by 9. And at 15 on the other side, we're going to add that by 9, because whatever you do on one side of the equation, you must do on the other side. This step is the completing the square step. This step right here is completing the square step. What did we just create out of nowhere? We created what's called a perfect square trinomial. That is what's created. Now that we have a perfect square trinomial, what can we do? Step 3. Factor. Factor the perfect square trinomial. And how do we factor that? What is x minus 9, x minus 6x plus 9? What does that factor into? And of course, 15 plus 9 is 24. So what is x squared minus 6x plus 9? What does that factor into? My people, what is x squared minus 6x plus 9? What does that factor into? It should be immediate. What multiplies to 9?
I was just having trouble typing it, but what's it called? It's x -3 and then x +3. So like in parentheses.
Yeah, be careful though. Are they opposite signs? Because if you have opposite signs,
Oh no, wait,
they
no, no,
don't, they
then it
don't
would
add
be
up to -6, right?
yeah, it would be the same. Negative and -3, -3. Because they
Right.
will multiply to 9.
Mm-hmm. So then when we do that, right? So when you factor it like that, x -3 multiplied by x -3, right? Instead of writing it like this, how should I write this instead?
X -3 squared.
There we go. Look at that. And so now we have x -3 squared equals 24. Didn't we do a problem just like this? Like before completing the square came up? We're using square roots. So now we're going to incorporate that here. So step number 4 is after we factored, now we use square roots. Use the square root step or technique, square root step or procedure. I'll say technique. Square root technique to solve for x. So here it's obviously permissible to take the square roots on both sides. When I take the square root of the left side, I get just x -3 on the left. But then I get the plus or minus term here for the square root of 24. I got the square root of 24. The square root of 24. What is the square root of 24? Didn't we discuss that already? We can break down the square root of 24 as square root of 4, square root of 6, x -3 plus or minus 2 rad 6. And now I can add 3 on both sides. And I get that x is equal to +3 plus or minus 2 rad 6. And there you go. We solved our original quadratic equation using the completing the square method, which was to make our, it really is to create a perfect square trinomial so that we can factor it as such, and therefore conclude this whole procedure by using square roots. So knowing how to use the square root method here is necessary to complete or to get to the solution of this quadratic equation. The key step, like we mentioned, is this step here, is adding half of the number in front of the x, adding the square of half of that number. Because this very step will always create a perfect square trinomial, always. That's how perfect square trinomials are constructed. Okay. Let's see some more of this in action. Get another good example here. Okay, something like this. What if I have x squared plus plus 2x minus 5 equals 0. So again, right, we have to add 5 on both sides first step. So the 5s here cancel. And I got x squared plus 2x. That equals 5. Then what do? We look at the number in front of the x, which is 2. What we're gonna do to it? We're gonna take 2, divide it by 2, and square it. Take 2, divide by 2, and square it. It's a lot of 2's here. But 2 divided by 2 is what? This really equals what? 1 squared? This really equals 1 squared. But what's 1 squared? It's 1. What do we have here? We have a perfect square trinomial. 5 plus 1 on the right side obviously is 6. Now what is x squared plus 2x plus 1? What does that factor into? X squared plus 2x plus 1. What does that factor?
X plus 1 all square.
Say that again?
X plus 1 all square.
Perfect, yes. So x plus 1, and that term is squared because it's a perfect square trinomial, and that's how it factors into. And then from here, what do? Take the square root on both sides, correct? We get x plus 1 equals plus or minus, don't forget the plus or minus 6, rad 6. And then we subtract 1 on both sides. And we get that x is equal to negative 1 plus or minus rad 6. And there we go. We're done. We're finito with the equation. We solve for x. Awesome. Fantastic. Great. Now, of course, even there are easier ones, right? Within the completing the square group of problems. There are easy ones, such as these are easy because, why is it easy? I would say the word easier. What makes this easy or simple to complete is because the number in front of the x is even. When we have an even number, right, we can divide by 2. So we're dealing with a whole bunch of whole numbers, even when we divide by 2, right? For example, in this one here, we got 6 divided by 2 is 3. 3 squared is 9. 2 divided by 2 is 1. 1 squared is 1. So in this scenario, in these two examples, right, we have these numbers in front of the x that are even. And so then what happens when I'm given a quadratic equation when that's not the case? Wait, this is minus 2. What happens when I have a scenario such as this one, where the number in front of the variable is not, it's not even, it's odd? Well, if I complete the square, right, I'm still going to add by 2 on both sides to get rid of that constant. So this is what I have, and I move a little space because I know I'm going to add something. I'm going to add by something. And it's something squared too, because that's the completing a square step, right? And what is that completing a square step? Take the number in front of the x. You can write -5, that's fine. Divided by 2. Okay. Now, square it. What do you get? I get x squared minus 5x plus positive 25 over 4. That equals 2 plus positive 25 over 4. And now this whole idea of fractions, right, just comes back. It comes back. So first, let's deal with the right side. Put the 2 over the 1. And now I have 2 fractions that I'm adding. I have these 2 fractions, different denominators. What do I do with the denominators? What must I do?
You multiply it by 4?
Top and bottom, right?
Yeah.
I multiply top and bottom by 4 because I must make the denominators both 4. So I get what? I get 8 over 4 plus, pardon me, there's no plus or minus, there's just plus 25 over 4. And when you add them, you get 8 plus 25. I get 8 plus 25 over 4, which is 33 over 4. So this is 33 over 4. So the right side, no problem. The right side is just adding fractions. Look at the left side, though. The left side is apparently, supposedly, a what? Perfect square trinomial. And now the big question is, what does that look like when you factor? When you factor such a perfect square trinomial, what is this going to look like? Does anybody have an idea?
Is it like x minus 5 over 2 all square?
You get a whole bunch of thumbs up. Yes! It's x minus 5 halves. How did you know?
I just 5 over 2 because I squared the 5 and I get 25, and when I squared 2 I get 4.
And then how do you know that those two numbers are the numbers that make the middle number work as well?
Well, I did my working out on my paper.
Right. So you see that? 5 halves, right? When you square it, it gives me 25 over 4. And then it has to be negative because negative 5 halves minus negative 5 halves, right? Minus 5 halves is negative 5, or I should say, negative 10 over 2, which equals negative 5, which is the middle term. So that's precisely the factorization, precisely. So this is what I have then, guys. Good, good. X minus 5 halves, parentheses squared, equals 33 over 4. And now I want to get x though. I still want to get x. So what must I do? I must apply the square root on both sides of the equation because I want to get rid of that square term on the left side. And so when I do that, I get what? I get x minus 5 halves. That equals plus or minus the square root of 33 over 4. Add 5 halves on both sides. I get that x is equal to 5 halves plus or minus the square root of 33 over 4. But can I break this down a bit? can I write this as square root of 33 over the square root of 4? And the square root of 33 I can't break down, so I'm just going to leave it as square root of 33. But the square root of 4 I can break down, and it's 2. And now what's nice about this is that I have the same denominators underneath the fractions. So I can combine the numerators, and I get what? I get 5 plus or minus the square root of 33 all over 2. And this is my final answer. X is equal to 5 plus or minus rad 33 all over 2. So the idea behind this example is that it's possible to apply the completing the square method to terms, to a scenario where the number in front of the x is no longer even, but actually odd. And the key step here, is from here to here. That's the key step. If you can do this, then you can do any quadratic equation problem. If that step makes sense to you, having this kind of perfect square trinomial looking like this, and factoring into this square of a binomial, then really you're able to solve any quadratic equation. Great. Great. So any questions? Any comments? Can I go over that step? Yeah. So that's the key step. So let me write it again, okay? So let me go back. So x minus 5. So this is a key step. If you know how to do this, everything will go well with you. Let's see. So we got x squared minus 5x plus 25 over 4. So how did we get here? We completed the square. So we already know this is a perfect square trinomial. We already know that. If we know that, then we know, or we should have an idea as to how to find the quadratic, the factor of the factored form of this trinomial. Let's say you don't. You have to think about two numbers that add to -5 but multiply to 25 over 4. But how did we get 25 over 4? How do we even get there? Isn't it exactly by multiplying by -5 over 2? Isn't that how we got it? So we know for a fact that -5 over 2 times -5 over 2 is 25 over 4. So I know that. I know this. Look, I know that -5 over 2 multiplied by -5 over 2, that equals positive 25 over 4. So the multiplication part works. Now, how about the sum part? What happens when we sum them together? What's -5 over 2 plus -5 over 2? Isn't that -10 over 2? But isn't that -5? And isn't that the middle number there? Isn't it? And isn't that exactly what we do when we factor trinomials? If possible, we find what two numbers multiply to the constant, but add to that middle term, which is exactly these numbers, -5 over 2. So that means I can write it like this. Look, x minus 5 halves multiplied by x minus 5 halves. But that is really x minus 5 over 2 squared. In the very step that we did when we divided by 2 and we squared it, that number, that -5 over 2, that number is precisely the number we put it into our factor. So in a way, we already know, we should already know the result. So I can do more of these. Look, I can do more of these. So let's do more of these, okay? Let's do more of the ones where the middle term is not is not an even number. So I want to complete the square and then factor at the same time. So when we complete the square, what's the step we do? We take the 3, and what do we do with the 3? We divide by 2, and then what do? We square, right? That's completing the square. The moment you do this step, apparently, supposedly, and of course you do, you create a perfect square trinomial. Now, we know that this equals x squared plus 3x plus 9 over 4. Now, what I want to do is factor this. This is a perfect square trinomial. Perfect square trinomial. What do we know about perfect square trinomials? It factors into something squared. That's what the perfect square trinomial becomes when you factor it. So what number is it when we let's say we don't know that, right? Let's say we want to do this thing again. What two numbers multiply to 9/4, and when you add them, give me positive 3? That number, you don't have to think too hard about that number. It's exactly this number here. 3 halves. 3 halves times 3 halves is 9 over 4. 3 halves plus 3 halves is how many halves? 3 halves plus 3 halves is 6 halves, right? So 3 halves times 3 halves equals 9/4. That's multiplication part. 3 halves plus 3 halves is 6 over 2, which is 3. So this is precisely, this number here is precisely the number. It's precisely it, which is exactly x plus 3 halves squared. You guys follow that? Do you guys see the pattern? Does that make sense, Sierra? What if I get this? Look, x squared plus 7x. Let's do that. What's the step? What do we add by to create a perfect square trinomial? 7 over 2 squared. This is a perfect square already. X squared plus 7x plus 49 over 4. This is a perfect square trinomial. Factor it. What does this factor into? We already know. X plus what? It's this number. It's this very number that multiplies to this, and when you add it to one another, it gives me 7. We should already know that this becomes x plus what? 7 over 2 squared. Does that make sense, Sierra? If not, no problem. If not, we can do more of these until you start to see the pattern. There's a pattern there. It's really just that number that we were squaring. That's precisely the number that should be in the factorization. Okay. Okay, and I'm gonna give you one more. One more of those curveballs, right? What if you have a scenario? So we're going to try to cover all different scenarios. We talked about when you have a factorable trinomial, just factor. If you have a squared term and a constant, square roots. If you can't factor, or if you can't use perfect square roots, the roots technique, then you do what's called perfect square trinomial, the complete the square method. And that's when you have scenarios where the x and the middle term, right? The middle term is even. So for some of you, you've seen it already. What happens if the middle term, the coefficient is not even? If it's odd, we can still do it. What if the quadratic has a number in front of the x squared? We haven't done that yet. So what happens there? Like, such as this equation here. Well, I still want to set it up in a way where I can still complete the square, right? So I want to complete the square. If to do that, I must have the x squared and the x term on the same side and the constant on by itself. So what I should do is subtract the 6x first, okay? Okay, then I get 3x squared minus 6x, put some space in between, and have a 1 on the right side. So this is what we have. This is the setup. Now, what do we normally do after we have this setup here? We take the number in front of the x, divide it by 2, square it. That's completing the square, right? But this okay. So when we have the scenario, in this scenario where the a value, right, or I should say the coefficient of x squared does not equal 1. So the moment when you have this scenario, the first thing to do, first step is to divide every term by the coefficient of x squared. So I can't do the completing the square step here. I can't because there's a 3 in front of the x squared. Because of that 3, I gotta get rid of that 3 first. So I need to divide everything. Divide by 3, divide by 3, and divide by 3. I must. So when I do that, the 3's cancel, and I'm left with x squared minus 2x equals 1 over 3. Now I can complete the square. Take 2, divided by 2, square it. What's 2 divided by 2? 1. 1 squared is 1. So I'm really just adding by 1 on both sides of the equation. X squared minus 2x plus 1 becomes what? What is x squared minus 2x plus 1? When you factor that, that's a perfect square trinomial. What does that factor into?
Is it x minus 1 all square?
Yes. Thank you. X minus 1 all squared. And then what's 1/3 plus 1? Well, 1/3 plus 1 becomes what? 1/3 plus 3 over 3. And 1 plus 3 is 4. So I got 4/3. So x minus 1 parentheses squared equals 4/3. And again, I still want to get x though. My primary concern is x. So how do I get x? I got to get rid of that squared term, right? That square exponent. To get rid of that square exponent, that exponent of 2, I must square both sides of the equation. I'm left with x minus 1 on the left side. And what do I get on the right side? I get the square root, I get plus or minus the square root of 4 over 3. Now let's worry about the square root of 4 over 3 a bit. That's equal to the square root of 4 over the square root of 3. What's the square root of 4? 2. What's the square root of 3? It's just square root of 3. But normally we don't like radicals in the denominator, so what must we do? We must rationalize it by multiplying by rad 3, the numerator and denominator. In the numerator, I get 2 rad 3. In the denominator, I get rad 3 over rad 3 times rad 3, which is rad 9, which is just equal to 3. So in reality, I got x minus 1 equals plus or minus 2 rad 3 over rad 3. So be careful with that. Be careful with having radicals. Be careful with having fractions in radicals. Be careful with having radicals in the denominator. The common prevailing wisdom is to always rationalize expressions with radicals in the denominator. And so when you do that now, I want to get x. So I must add by 1 on both sides. And I get x is equal to 1 plus or minus 2 rad 3 over 3. And of course, we don't like to just leave our expressions like this. We always want to make it nice, compact, with a single fraction if possible. So that 1 can be rewritten as 1 over 1. So I got 1 over 1 plus or minus 2 rad 3 over 3. I must have the same denominator, the 1 and the 3. So the least common denominator is a 3. So multiply top and bottom by 3. And I'm left with x is equal to 3 over 3 plus or minus 2 rad 3 over 3. Same denominator, combine the numerators. 3 plus or minus 2 rad 3. And I'll divide all of that by 3. So just to write it again, my solution here, my roots, the solution, the zeros. I'll just write it as together. So x equal to plus or minus 2 rad 3 over 3. Any questions, guys? Any comments? Concerns? So this is completing the square. I think we've covered every possible scenario, from the simplest of the completing the square kind to the more complex ones with odd numbers in front of the x, to numbers that make the x term value, right, the x term coefficient bigger than 1. So these are all the possible scenarios that may appear, and you should be able to deal with all possible scenarios using the completing the square method. And let's say you don't remember the completing square method, and you don't remember factoring. The one that always works, the way that always works is the quadratic formula. So the quadratic formula always works. Even when the solutions are not real, you may have imaginary solutions, but of course we're not dealing with that in this class. Even that, this works as well. Okay, and then let me just say something. The quadratic formula, how do we get there? First of all, does anybody know the quadratic formula by heart? I'm pretty sure some of you do, right? Jalen Spears raised hand. Yes, Jalen.
Isn't it negative b plus minus square root b squared minus 4a squared over 2b? I don't know that. I can't remember that part.
Yeah, it's over 2a.
Okay.
And you said 4a squared, it's 4ac.
Okay.
No problem. Thank you, though. This is the quadratic formula. Okay, and what does the ABC stand for? That's when you have the equation, the quadratic equation, in standard form. What's the standard form of a quadratic equation? It's ax squared plus bx plus c equals 0. So when you have a quadratic equation written in this way, you should be able to identify a, b, c, and plug it in to this formula, and you get the answer every time. All of these problems that we just did, all of them, I can use a quadratic formula and get the same thing. I can get the same thing. All of them. Just use this instead. I just want to end with this though. The quadratic formula to some of you just seem to just fall out the sky. That's what it is. That's what my teachers told me. It just works. But I hope, maybe not, I don't have time to do that today. But I'll say this does not come from out of nowhere. You can actually show how you get this to be true. And the way we get to this is by using the completing square method. The completing square method, if you use it on this equation and you apply the same steps that we just did, but now we're dealing with variables instead of numbers, and we have letters instead. If the completing square method to this equation, and that will be a challenge to anybody, if you can do that and solve for x, you get exactly this. So the quadratic formula is not just a made up formula that somebody figured out to work out of. Someone used the completing square method to derive it. Okay, great. So stop right here.